Hello everyone, welcome back to Civil Learning Online, and today in this video I am going to discuss about Cayley-Hamilton theorem. In this video, first of all I will discuss about what is the meaning of Cayley-Hamilton theorem, and then we will dive into a numerical in which we will first verify the statement of Cayley-Hamilton theorem, and then after we will see the application of Cayley-Hamilton theorem, which is about how to find the inverse of a matrix using Cayley-Hamilton theorem. So without any further delay, let's get started. So let's begin the solution of this numerical problem, and here we are asked to verify Cayley-Hamilton theorem for matrix A and find the inverse of matrix. Suppose this is matrix A and we are asked to find the inverse of this matrix, and before that we are asked to verify Cayley-Hamilton theorem. So first of all, make you familiar with the concept of or the statement of the Cayley-Hamilton theorem, and then after that we will proceed with the solution of this numerical. And on solving this numerical, this method is going to be more clear to you. So it states that every square matrix satisfies its own characteristics equation, and the characteristic equation is A minus lambda I determinant, means determinant of A minus lambda I equals to 0, where A is the given matrix, lambda is any scalar quantity, I is identity matrix of order of matrix A. If our matrix A is of 2 by 2 order, then identity matrix is also I is also identity matrix of 2 by 2 order. If it is of 3 by 3 order, then it is then I is also identity matrix of 3 by 3 order. And we have supposed that square matrix is A, and for square matrix A we have the characteristic equation A determinant of A minus lambda I equals to 0, and on solving this characteristic equation we will get a polynomial of the form lambda q minus or plus, suppose this is just an example, 5 lambda square plus 4 lambda equals to 0. And on replacing lambda with A, if we replace lambda with A of this polynomial, then it satisfies this equation. We will get 0 at the end, and it verifies this theorem. And so this was about the statement of Cayley-Hamilton theorem. And if we talk about its application, so the Cayley-Hamilton theorem is basically applied for finding the inverse of given matrix. And in this numerical, I have told you about the statement, and further we will solve this numerical, and this statement will get clarified to you, and we will see how we will find the inverse using this theorem. So let us move toward the solution now. So we will write here solution, and we will begin with a same characteristic equation, and that is A minus lambda I determinant equals to 0. Now what we will have here, we will write the matrix as it is. So draw the sign of determinant and matrix here 1 4, and this is 1, so write it 1, and 3 2 2 7 3 1, and again lambda I is identity matrix, so diagonal element will be unity and remaining other element will be written as 0. So we will have here 0 0 and 1, and draw the sign of determinant again, means bracket. So now we will need to resolve this. So we need to multiply lambda with each and every element of this identity matrix, and then we will subtract that. So on doing so, we will get here 1 minus lambda and remaining other element will be written as it is. Similarly, we will have here 4 2 minus lambda, and here it is 3 as it is. Similarly, 1 2 1 minus lambda, and draw the bracket for determinant. Now what we need to do is we have to find a determinant either using this row or this column. It is up to you. So on doing so, we will get a form here. Let me write it here, 1 minus lambda. So what we will need to do is we have to cover the row and column in which this element lies. We are calculating the determinant with respect to 1 minus lambda, so cover this and this. So what we'll do is we have to multiply, take positive sign while multiplying downward and negative sign while multiplying upward. So we will have here, let me start a bracket, 2 minus lambda times 1 minus lambda. This is sign of multiplication, and minus 2 times 3. These two positive and this negative. So 2 times 3 is 6. Close the bracket. Similarly, we have second element, that is 3. I am using this moving according to the row. So we have 3. So we will write here minus 3. Use the sign of cofactor. So minus 3 times, again start the bracket, minus 3 times, cover the element in which this 3, cover the row and column in which the element 3 lies. So this and this is covered, and remaining we will get 4 times 1 minus lambda. So start the bracket, 4 times 1 minus lambda, and minus 1 times 3. So again close the bracket, and sign of cofactor is positive for 7. So plus 7 times, again start the bracket and cover the row and column in which the element 7 lies. So this column and this row is covered. So we will have here 4 times 2 means 8 minus 1 times 2 minus lambda. I hope you got it. So on solving this, we will get it in the form of lambda q minus sum of diagonal element times lambda square plus sum of cofactor of diagonal element times lambda minus determinant of given matrix. We have represented it as A, so determinant of A equals to 0. Either you can multiply or you can simply use this line. So use what you need to do is you have to write this, omit this, and again simply use this formula, because when we solve this, we multiply this one by one, we will get this form. So now I am going to teach you how to find the sum of the diagonal element, sum of the cofactor of the diagonal element, and determinant of A. So let's move further. So right here equals to, and we have first variable as lambda q minus sum of diagonal element. In bracket we have sum of diagonal element, and diagonal elements are the elements lying along the diagonal. So it is 1 plus 2 plus 1, we will get 4. So 4 times lambda square. Now we have the sign of plus here, you can see refer to this formula. So here it is plus, so right here plus, and we have sum of cofactor of diagonal elements multiplied by this lambda, sum of cofactor of diagonal elements. So we have to find the cofactor of this diagonal elements, means first we will find the cofactor of 1. So we need to cover the element row and column in which 1 lies. So here we go, this and this. So we will have remaining element as 2 2 3 1, right? Let me write it on the side of this page as a rough. So we will have 2 2 3 1. Another, we have another diagonal element is 2. So cover the row and column in which 2 lies. So this and this is needed to be covered. So we will have here 1 1 7 and 1. What I said, 1 7 1 1. Okay, now we have another element, that is 1. 1 is also diagonal element, so cover row and column in which 1 lies. So this and this needs to be covered, and we will have here 1 4 3 2. So we will have here 1 4 3 2. And now what we need to do is we have to multiply. So 2 times 1 is 2, minus 3 times 2 means minus 6. We will have here minus 4. Similarly, we have 1 minus 7 minus 6. Similarly, we will have here 1 times 2 is 2, minus 4 times 3 is 12, means we will have here minus 10. So sum of minors of the diagonal element is going to be 10 6 4. Sum means minus 20. So we will have here minus 20 lambda. Now we need to find a determinant of matrix A. So if we find a determinant of matrix A, how we are going to find it? See here, we have matrix A. So 1 times we will have here, let me use this page as rough. So we have 1 times 2 2 3 1 minus 3 times. Simply step is same, the element in which the row and column in which the respective element will lie, we will cover that and we will write the other elements, and then we will do the further operation. So 3 lies in this row column and this row. So 4 1 3 1 is visible here. So 4 1 3 1 and put the positive sign here, and now it is time to multiply with respect to 7. So 7, and the elements which are visible is cover this and this. We will see 4 1 2 2. So we will write here 4 1 2 2, and on solving this, again downward positive, upward negative. So on solving this, we will get the determinant of this matrix as minus 30, sorry, we will get positive 35 here, positive 35, and according to the formula we need to write the determinant minus 8 times. So minus, right here, minus 35 equals to 0. Now as per the statement of Cayley-Hamilton theorem, what we need to do is we have to replace the lambda as A. So we will rewrite it as AQ minus 4 A square minus 20 A minus 35, and simply multiply this 35 with identity matrix. It won't create any problem, and further it will help us to solve this numerical easy, because these all will get converted into matrix form. So we will, here it is nothing, means we will write here identity matrix. And what we have done here, we have replaced lambda with A, means replace lambda with A. Now we need to find the 3 cube of A, matrix A, and square of matrix A. For that we need to have a good concept about matrix multiplication, and I hope you know how to do the matrix multiplication. If not, you can watch the video which is provided in the I button about how to do the multiplication of 3 by 3 matrix. So let me show you a little bit. So A square means A times A. So we have to multiply the same matrix A with A. So matrix A is 1 4 1 3 2 2 7 3 1, and multiply this with same matrix A. So we will have here 1 4 1 3 2 2 7 3 1. So on multiplying this, we will get, on A square value we will get 20 23 23 15 22 37 10 9 14. How we got this? See here, we have to multiply this 1 with 1 and plus 3 times 4 plus 7 times 1, we will get 20. Similarly, how we got 23? 1 times 3 plus 3 times 2 plus 7 times 2, we will get 23. Similarly, for this 23, 1 times 7 plus 3 times 3 plus 7 times 1, we will get 23. Similarly, 4 times 1 plus 2 times 4 plus 3 times 1, we will get 15. Similarly, now after getting the value of a square, we will move for aq. So simply multiply the value of a square with a, we will get the value of aq, because aq is a square times a. We have got the value of a square, so we will multiply this value again with the value of a, matrix A. So we will get aq, and aq value is going to be, we will get aq as 135, 152, 232. I hope it is visible to you guys now. Similarly, we will get 140. Just you need to have a basic knowledge about the matrix multiplication of 3 by 3 matrix, and that's gonna be easy to you, and you can refer to the previous video, which is link is in the description, about how to do the multiplication of 3 by 3 matrix. You will easily calculate these values. So I have shown you. Now we will simply rewrite the value here, and we will check if whether we are getting null matrix or not. So we have got the value of aq as 135, 152, 232, 140, 163, 208. Similarly, 60, 76 and 111, 111 minus 4 times a square, and we have the a square value as 20, 15, 10, 23, 23, 22, 37, 9 and 14. Again, minus 20 times a, I am going to write it here, minus 20 times a, and matrix A is 1 4 1 3 2 2 7 3 1 minus 35 times 1 0 0 0 1 0 0 0 1, and on solving this we will get it as, let me show you one and then see here. What we need to do is, further 135 minus 4 times 20 minus 20 times 1 minus 35 will be equals to 0. Similarly, 152 minus, we will multiply each and every element with this number, 4 number which is lying outside the matrix. So 4 times 23, 152 minus 4 times 23 minus 20 times 3 minus 35 times 0, we will again get here 0 0 0 0 0 0 0 0. So at the end we will get null matrix which is equals to 0, and this was the verification of the Cayley-Hamilton theorem. Now we will find the inverse, and how we will find the inverse using the Cayley-Hamilton theorem, see here. So we here we had got the polynomial expression as aq minus 4a square minus 20a minus 35i equals to 0. So in order to find the a inverse, what we need to do is we have to multiply this expression, polynomial expression, with a inverse. So on doing so, on multiplying aq minus 4a square minus 20a minus 35i equals to 0 with a inverse, we will get here a square minus 4a minus 20 minus 35 times a inverse equals to 0. So what we need to do is we have to bring this A inverse minus 35 A inverse to this side. So we will have here 35 A inverse, this negative on going that other side of the equal to sign, then it will get positive. So 35A equals to A square minus 4A minus 20. Now we will write the matrix A value which we had calculated, that is a value of A square. So A square value was 20, 15, 10. Similarly 23, 23, 22, 37, 9, 14. This was the value of A square minus 4 times A, and the value of A is 1, 4, 1, 3, 2, 2, 7, 3, 1 minus 20. Nothing here means I. So write here identity matrix, and that is 1, 0, 0, 0, 1, 0, 0, 0, 1. This is because we cannot simply subtract 20 from each and every element, but when we write identity matrix means we come to know that from which element we are going to subtract 20. Now here we need to do the simple multiplication of the matrix. This 4 is going to multiply each and every element of this matrix. Similarly 20 is going to multiply each and every of this element of this matrix, and then we will need to subtract this 2 matrix from this element. So on doing so we will get here minus 4, 11, minus 5. I hope you know the simple matrix addition subtraction. That is what we have done here. I will show you one example here. Minus 1, minus 6, 25, 6, 1 and minus 10. So we have got 35 A inverse equals to this much. How we got this minus 4? See here, we have first element as 20 minus 4 times 1, 4 times 1, and minus 20 times 1. We will get here minus 4. I hope you understood. Now for this element, let me show you. For this element we have 15 here, so 15, right here 15. We have to subtract corresponding elements only. 15 minus 4 times 4, 4 times 4, minus 20 times 0, minus 20 times 0. We will get here minus 1 on solving this. This is how we got value of each and every element. So now here for A inverse, what we need to do is we have to divide, because this is in multiplication. This will get that side, then it will get divided 1 by 35 times minus 4, minus 1, 6, 11, minus 6, 1, minus 5, 25 and minus 10. So on dividing this we will get minus 4 upon 35. You can leave it up to here also, or you can do one more step, that is divides each and every element by 35. Like multiplication, we multiplied each and every element with the number which was lying outside the matrix, and here for division also we will do the same. So minus 4 by 35, 11 by 35. Similarly we will have here minus 5 by 35 means minus 1 by 7, minus 5 upon 35, so 5 7 times 35, so minus 1 by 7. I hope you got this. Now further we will have here minus 1 upon 35, minus 6 upon 35, 5 upon 7, 5 times 5, 5 times 7, so 5 upon 7, and here we will have here 6 upon 35, 1 upon 35 and minus 2 upon 7, and this is final solution. We have got the A inverse of the given matrix A, and I hope this video was helpful to you, and if you have any kind of confusion in any step, feel free to write me on my email which is provided in the description, or you can directly comment on this video. I will help you as possible, and do watch the video. If you have any confusion about how to do the matrix multiplication of 3 by 3 matrix, link is in the description. See you in the next video. Till then, stay safe and take care of yourself.